morning, everyone. I'm Ha-Myung Park from KAIST, Korea. There are many people, so it makes me very nervous. So if the presentation is not good, please understand me. Okay. Then the title of this presentation is Enumerating Trillion Triangles on Distributed Systems. And this work is co-authored by my two advisors, Ha-Myung and Yu-Kang. I will first introduce the problem, triangle enumeration, and its importance. The triangle enumeration problem is to enumerate all triangles in an undirected simple graph. For example, here is an example graph, and there are 5 triangles. And they are exactly the output of the triangle enumeration problem. And the triangle enumeration has been regarded as very important problem because it is a core module of many graph mining algorithms, and also the triangle enumeration itself has many applications related to anomaly detection. However, the real-world graphs, such as friendship network in social networks or web graph, are tremendously large. So it is very hard to find all triangles in such very large graph. Then the question is that, how can we enumerate all triangles in such very large graph? Recently, several algorithms are proposed for the problem. They are shared memory systems and MapReduce algorithms. The shared memory systems show very fast performance because they use memories, but they cannot process large graphs that do not fit into the shared memory. Meanwhile, the MapReduce algorithms show very good scalability. That means they can enumerate triangles in very large graph. But practically, they show very slow performance because they generate and shuffle very massive intermediate data. Okay, now I will briefly introduce one of the previous MapReduce algorithms. When each vertex has a color, a triangle can have up to 3 colors because a triangle has 3 nodes. Then there are 2 facts. First, any triangle with 1 or 2 colors must exist in an induced subgraph on vertices with 2 colors. And second, a triangle with 3 colors does not contain any edge with 1 color. That means intra-edge. According to the 2 facts, the previous MapReduce algorithm generates 2 types of subgraphs and find triangles in each subgraph in parallel. However, the problem is that the previous algorithm shuffles too many edges for generating subgraphs. In the MapReduce system, shuffling data requires very heavy disk and network I/O and require to sort the whole data. Thus, massive amount of shuffle data makes the system very slow. When low is the number of vertex colors, each edge is shuffled low -1 times as an edge exists in low -1 subgraphs. And thus, the total amount of shuffled data is low -1 times the number of edges. When the data is very large, the size of shuffled data is prohibitive. Then, how can we reduce the amount of shuffled data? That is the question. Then we answer the question by proposing our algorithm. The key idea is that subgraphs require each set of edges as a unit, where Eij means a set of edges whose end vertices has color I and j. Then according to the key idea, PTE, the proposed algorithm makes the set of edges first, and then it does not shuffle any data for generating subgraph. The graph partitioning of PTE is done by a MapReduce round, shuffling the entire edge of the input graph. After graph partitioning, PTE generates subgraph by leading the edge set through network. Then we find all triangles in each subgraph in parallel, like the previous MapReduce algorithm. Then now I compare PTE with the previous MapReduce algorithm. The previous MapReduce algorithm shuffles low times the number of edges for generating subgraph, as I just said. But the PTE does not shuffle such kind of data. Actually, the size of shuffle data by PTE is only the number of edges. Instead, PTE requires low times the number of edges network lead. Note that network lead does not require heavy disk I/O and does not require to sort the data like shuffling. So it is very light operation. And this figure shows the amount of shuffle data according to the data size. As you can see, the PTE shuffles up to 245 times smaller data than CTTP, the state-of-the-art MapReduce algorithm. And the gap increases as the graph size increases. Now I am going to show a little bit different aspect. That means previous MapReduce algorithm performed redundant computation when finding triangles in each subgraph. As mentioned, the previous algorithm generates two kinds of subgraph and find triangles in each subgraph. The first kind of subgraph includes induced subgraph on vertices of two vertex colors, and the second kind of subgraph includes induced subgraph on vertices of 3 colors without intra-edges. Then let us see more details on the second kind of subgraph. Given a subgraph, previous algorithms find triangles by intersecting neighbors of 2 vertices in each edge. In this example, given an edge u, v, by intersecting the neighbors of u and v, the previous MapReduce algorithm finds the triangle u, v, and b. However, the vertex A and N in the example cannot make a triangle with the edge u, v because the subgraph with 3 colors has no intra-edge. In other words, we only have to check the neighbors whose color is not the same as the color of the edge u, v. The proposed algorithm PTE exactly worked like that. We removed the redundant computation by considering the color of subgraphs. We assume that an edge have a direction according to the total order of vertices. Then let E star ij be a set of edges whose start vertex has color I and end vertex has color j. Then for finding triangles containing an edge uv of color ij, PTE intersect the neighbors of u in E star ik and the neighbors of v in E star jk. Accordingly, finding triangles in a subgraph with 3 colors is divided into 6 subproblems according to the color directions. Here, we introduce second optimization. We reduce the network traffic by scheduling computation. In this figure, the check marks means which subproblem requires which edge set, and the shaded area represent when an edge set should be in the main memory. The previous algorithms should retain all the 6 edge sets in the main memory for solving the 6 subproblems. But PTE restores up to 5 edge sets at a time by scheduling these subproblems, as you can see in the table. Each edge set contains E over rho square in expectation, and the 5 edge sets of size 5E over rho square should fit into the main memory of size M. So as the amount of the network lead is rho times the number of edges, the network lead is reduced by root 6 over 5 by this optimization. Okay, now I'd like to show the experimental results. We focus on answering the following questions. The first question is, how much do the 3 methods of PTE contribute to the performance improvement? And the second question is, how does PTE scale up in terms of the number of machines? And the last question is, what is the result on the real-world graphs? As we show the left figure already, the pre-partitioning technique reduces the shuffle data by up to 245 times, and the decreased shuffle data significantly affect the running time. And the running time is depicted in the right figure. And the 2 optimizations bring relatively minor performance improvement compared to the reduced shuffle data, but they are not negligible. And this figure shows the running time versus the number of machines. As the number of machines doubled, the running time of the PTE decreased by about half. It means the machine scalability of PTE is almost ideal. And this figure shows the running time of various algorithms on various real-world graphs. And the PTE show up to 47 times faster performance than the state-of-the-art MapReduce algorithm. Moreover, only PTE succeeds in processing the largest data with 3 trillion triangles. And this is the summary. In this presentation, we addressed the triangle enumeration problem on very large graph. And our approach was decreasing shuffle data and total work and network traffic by pre-partitioning the graph and considering the color direction and scheduling computation. As a result, we succeed in enumerating 3.1 trillion triangles from a very large graph with 6.3 billion vertices and 72 billion edges. And this is the end of my presentation, and thank you for listening.
Can your algorithms be modified so that we can identify pairs by connecting whom we can form triangles? Like the triangle closing arguments?
Sorry, can you speak louder?
So your algorithm suggests ways of finding triangles very fast, right?
Yes.
Now, can you suggest algorithms using which we can find pairs of nodes? Like
pairs?
Like pairs of vertices?
Partition.
Or like
pairs.
Pairs
okay.
of vertices, so that if we connect them,
Yeah.
triangles will be formed. Like,
Yes.
like triangles that can be closed by adding one edge. Can you modify your algorithm to find those?
You mean if you find all wedges, which means the 2 lengths pass, then if you join the edges, you can find triangles. You mean
Right.
this? Okay. Also, there is an already proposed an algorithm work like that, but if we find using wedges, we should find all the wedges and in very large graph there are so many wedges, so it should make very many intermediate data.
Yes.
So it will be inefficient. Okay.
Okay.
Hi, thanks for the talk. It's not a problem that I'm that familiar with, so I might have missed this at the beginning. But are the colors on the nodes,
Yes.
are they just like assigned randomly for the purposes of this particular task?
Exactly, we color the nodes randomly.
Okay,
Okay.
cool. Thanks.
Thanks. Thank you.